Hi, welcome to Algebra 1 with Miss Andrea. Today we're going to go over the review worksheets that we were given from the module. Now this is Module 7 in the book, or the online book rather, which is also known as Unit 5. And its title, just so we're sure we're on the same unit, is Comparing and Contrasting Functions. So let's get right to it. We have three different questions here. They're asking us whether they're linear, quadratic, or exponential. And the first one has to do with how it's written as an equation. So let's think about what is our format for a linear equation. It's y equals mx plus b. What is it for quadratic? Y equals ax squared plus bx plus c. This one was linear. I'm going to give us 2 for quadratic just to be safe. Our other one was y equals a times h minus k. Excuse me, that's not h minus k. X minus h squared plus k. Those are both quadratic. Then our last one is y equals b to the power of x, and that one was exponential. So let's look at our equations that we have over here in number 1. Y equals 5 to the power of x. That looks right here like this one, exponential. Okay, then we have y equals x squared plus 2x plus b. That's in this standard format right here. So that one's quadratic. That means this one must be linear, but let's make sure. Y equals mx plus b. Oh yeah, that one's definitely linear. All right, so now we need to look at these charts and determine. Well, remember, for it to be linear, you must have a constant difference at level 1. To be quadratic, you're going to have a constant difference at level 2. And then for it to be exponential, you're going to have a constant ratio. Now, what do those mean? Difference means that when we look at the y values, and you add or subtract to the number before it or after it, is going to be the same each time. So if we add 2 every time, or add 10 every time, or subtract 5 every time, those are constant differences. A constant ratio means you're either going to be multiplying or dividing to get to the next one. So if you multiply by 5 and multiply by 5 and multiply by 5, that's going to be a constant ratio. So let's look at these. 30, 20, that's the difference is 10, 20, 12, difference is 8, 12 and 6 is 6, 6 and 2 is 4, 2 and 0 is 2. I can already say this is definitely not linear because this is difference 1, right? That didn't work out for us. So let's look at difference 2 and see if that's going to work out. 10 and 8, the difference is 2, 8 and 6 is 2, 6 and 4, 4 and 2. So difference 2 is consistent or constant. And so this one is going to be a quadratic. All right, so let's look at this. 4 and 8 is 4, 8 and 16 is 8, 16 and 32 is 16, 32 and 64 is 32. I see a pattern here. It's going up by the same amount. So what's actually happening here is it's being multiplied by 2. 4 times 2 is 8. 8 times 2 is 16. So I'm not even going to look at the second difference. 16 times 2 is 32. 32 times 2 is 64, and so on. So which one was times? A constant ratio. So this is exponential. All right, so that means this one must be linear, but let's look at the differences to be sure. 11 minus 9 is 2. 9 minus 7, 2. 7 minus 5, 2. 2, 2. All right, so this one is definitely linear as well. So we did well with those. Now let's look at these graphs. Is the graph of this a linear or quadratic function? Well, this one is linear because it's a straight line. This one's a parabola. That means that's quadratic. What does an exponential graph look like? Well, we have exponential increase and we have exponential decrease. So there you go. All right, decide whether each of these word problems represent a linear function or quadratic. Remember, we were only dealing, when we got into this type, when we studied this before, it's either linear or quadratic, linear or exponential. We didn't get into the quadratic here. So a library has, and we're supposed to write a function. Our functions were, we had y equals p times, not times, let's say, plus the difference times t, the time. So p is the principal or the starting amount, and then you're adding the difference times the time. This was the linear version. And then if you want the exponential, there are a couple of different formats. You're going to have y equals a times 1 plus or minus r to the power of t. So plus or minus, those are your differences right there. If it's growing, it's plus. If it's getting smaller, if it's exponential decay, it's going to be minus. Now, sometimes that 1 is already built into the rate or the ratio. So we need to be careful with that. So for example, if you're doing, if something is doubled, then you don't need to add anything to it. You're just going to put a 2 there. Whereas if it's an account that increases by 5% every month, you do 1 plus 0.05. Okay, so you just have to watch the words and see what it is that you're going to be coming across. All right, let's look at this. A library has 8,000 books and it's adding 500 more each year. Adding, keyword there tells me it's going to be linear because it's going to have a constant difference between adding and subtracting, right? It's going to be an arithmetic sequence for the output values. So y equals our beginning amount, 8,000, plus our difference, 500, times t, or time. And since this is y, we could have put an x there, but I like t because it represents time. All right, a bank account starts with $10. Every month, the amount of money in the account is tripled. Well, tripled is a multiplication word, so that must mean this is exponential. And our formula starts with the original amount, $10, times. Now, since this is tripled, we don't have to add it to the 1 because it's not a specific rate for like interest rate. So we can just go ahead and put 3 there, and it's raised to the power of t. So for the first month, so you start at month 0 with $10 because 3 to the power of 0 is going to be 1. 10 times 1 is just $10. Then month 1, 3 to the power of 1 is 3. 10 times 3, $30. Then the second month, 2, 3 to the power of 2 is $90. 10 times 9 is 90, right? So you can see that that function works. All right, which is a true statement about the data shown in the tables? Both tables are linear. Well, I don't know that yet. So let's see. 4 to 5 is 1. 5 to 6 is 1. 6 to 12 is 6. But look, it's not 3 to 4 here. It's 3 to 9. Okay, so you have to keep that in mind. That's a trick right there, because you have to, when you're comparing the y values, if the x values aren't increasing by 1, then you can't consider the y's by themselves. You have to take them in account with the x's as well. So let's see, 3 to 9, we're missing 4, 5, 6, 7, and 8. Right? That's a whole bunch in there. How many is that? 1, 2, 3, 4, 5. 5 different places. So I bet this is linear. I bet if we had 4, it would be what? Let's see if it goes up by 1. 7. 5 would be 8. 6 would be 9. 7 would be 10. 8 would be 11. And 9 would be 12. So this was a tricky one. They were specifically trying to trick you by having a jump right there, okay? And then 12 goes on to 13, the difference is 1. So we have a constant difference of 1 when you compare all of your x values going up by 1. So this one is definitely linear for sure. And then let's look at this other one. 0, 1, 2, 3, 4. I'm not going to let them trick me again. All right, so these, all our x values go up by 1, so I want to look at my y values. 0 to 1 is 1. 1 to 4 is 3. 4 to 9 is 5. 9 to 16 is going to be 7. So this one is not linear. Let's look at the second difference. 7 and 5, the difference is 2. 5 and 3, the difference is 2. 3 and 1, the difference is 2. So it looks like this is quadratic because difference 2 was consistent. All right, so both tables are linear. We know that's not true. Only table 1 is linear. That one's true. Only table 2 is linear. Not true. Neither table is linear. So B is the correct answer. Determine whether the given function is even, odd, or neither, and explain why. All right, well, even means it can be folded across this line right here, which would mean if we drew this graph, let's see, it goes down there, and this one would go like that. If we drew that, it would look, my lines would end up right on top of the blue ones. If we folded this in half, it would have laid right on top of each other, but it doesn't. So this is definitely not even. Now, odd is the same thing as about the origin. Or if we were to take it and rotate it, shoop, then it would be the exact same graph's exact same picture. Well, the easiest way to look at that is to flip it over the x and then over the y. So if we flip this over the x, and I guess I'm skipping A and B and jumping straight to C, so we'll get back to A and B in a minute. But if we were to flip this over the x, like this, and this one like that, and now we need to, I'm going back to orange, flip it across the y. So my yellow is going to flip across the y, and look, it ends up right back on top of the blue. So this one is going to be odd. Okay, so we flip it across the x, then we flipped it across the y, and it ended up exactly where it started. So that's considered odd. All right, so now when it's in its equation format, what you have to look at is how the variables and what their exponents are. If all of the variables are even, then you have an even symmetry. If all of the variables are odd, you have an odd symmetry. If you have a mixture of them, then you have neither. So let's look at this. This is 2. And what is this? The variable is raised to, if we don't have a variable there, it's raised to the power of 0, which is considered even. So this is 2 and 0 we'll call even. So this is an even function. All right, so let's look at this one. That's an 8, a 4, a 2, and an x with a 0 is also even. They're all even. 8, 4, 2, 0 is even. What would an odd equation look like? It would look like something like x to the third plus x. You probably have some coefficients in there, but this x is to the power of 1, and there's a 3 there, so that one would be odd. All righty. Our next one here. Examine the graph from the left from point x is 0 to x is 1 right here. So that another way to write that would be like this, right? Determine which graph is growing faster by finding the rate of change for each graph. Okay, so x is 0. They're both going through the point of origin, and x is 1. We've got one right here and one right here. Well, let me actually, I'm going to put these in 2 different colors. I'm going to do the line in orange and the exponential graph in yellow. So for this one, we've got the yellow. We go the change in y or vertical change, over the change in x. So we're going to go up 1 for the y and over to the right 1 for the x value or horizontal value, and that is just 1. So the value for our function r is going to be 1, the rate of change. Okay, so now let's look at the straight line rate of change. We go up 1, 2 for the change in y, and the change in x is only 1. So that translates to 2. So which rate of change is going to be a larger, which graph is growing faster? It's going to be the s function or the linear function, right? Okay, well, now let's look at, I'm going to erase these. Let's look at the next question. It says, look at it from 2 to 3 and see which one's growing faster. So we've got the exact same question. 2 is right there and 3 is right there. And then I'm going to do in purple here, 2 and 3. All right, so let's look at these. The green, 1, 2. So the vertical change is 2 in the green, and it's 1 horizontal change over 1 equals 2. So in our exponential function, which is the r function, it is changing by a rate, its rate of change is 2. And then in the linear function, let's look at this, 1, 2, 2 up, and 1 over. Oops, but it's a 1. So that's 2 as well. So which graph is growing faster? The answer is neither. They're growing at the same rate. Okay. I don't think I can get that last one in there. So we'll just look at this one. All right. The value of a car in dollars, f of x, depreciates after each year x. The following table shows the value of the car for each of the first 4 years that it was purchased. So we purchased a car new at $22,000. After the first year, it was valued only at $19,000. Year 2, $16,000, and so on. So we're supposed to, it looks like, find the common ratio for both functions. So how do we find a common ratio? Do you remember what I told you? Well, you can either multiply or divide. Well, since I don't know what to multiply 22,450 by to get 19,307, I think I'm going to divide. So I'm going to start at the down here, 12280.33 and divide by 14279.46. And I get it retained about 85% of its value, 86% of its value, because I get 0.8 8599999. So actually, I think I'm going to, let's see, I'm going to divide downwards. So 22,450 divided by 19307 is 1.1627. So it looks like it's losing about, let's see, it's losing about 15% of its value each time. Let's do another division problem just to be sure. Because when I went up, right, it was 0.859, which is approximately, what, 86%? So it retained 86% of its value, retained value. And when I went down, it was 1.1627. So that's approximately, you have to remember when you're, our exponential function, was y equals a times 1 plus or minus r to the value of t. So you have to remember you're adding or subtracting 1 to whatever our rate is, right? So this is if we subtract that 1 there, this is losing approximately 16% decreased value. And then that makes sense because 86%, 86 plus 16, that's about 102. So my rounding is a little bit off. You could say it's about 15%. And make it a little bit easier numbers, 15% and 85%. So the value of a second cart is modeled by the what's the question? Find the common ratio for both functions, 15%. The value of the second cart is modeled by the equation where g of x represents the value of the car after. So it's the same. This is 84%, so that's 16% here. Because it's going down by 16% because they did 1 minus 16 in order to get that 84 right there. So when you plug 1 minus 0.84, 0.16 equals 0.84. So that's how they got that right there. So that's 16%. So it looks like it's the same. I just, when I rounded here, I took it down to 15% and 85%, but I should have just taken this one down. So, or kept that one the same and taken this one down. But 15%, 16%, they look like they're depreciating at about the same value either way. It's not like one car is going down by 1% and the other is going down by 75%. So they're pretty equally matched cars there. All right. Sally and Sam are testing out their new potato shooters from their tree house, which are at different heights. The chart to the right shows the time in seconds and height in meters of the potato pieces from Sam's shooter. The time, t, and height of Sally's potato shooter can be represented by this equation. So using this information, answer these questions. Whose potato pieces went higher? Well, remember we have time and height, and they go like this, right? So up here is the vertex, the point at which it no longer is going up and it changes and starts to go down. That's the vertex. So we need to find the vertex to know the total height. If you look at Sam's, we're going to start with Sam's because it's easier. The y values, the height, are going up and up and up, and then they start going down and down and down. So his vertex is somewhere right about here, which I'm going to say is 1.25 and 10.5. And this is just a guess based on the patterns that I see. 7 to 9, 7 to 9 to 10. It could even be 10.25. So 7 to 9 to 10 to 10.25, back down to 10, 9, 7, 4, 0. And it's at 1.25 seconds because it's right in between 1 and 1.5 seconds. Okay. So this is going to be the vertex about that time. Because remember, it's just my guess. It's not, I didn't do math to figure that out. It's just an educated guess. All right. So Sally's shooter is, in order to find the vertex, you do negative b divided by 2a. So negative b is going to be negative 4 divided by 2 times negative 1. Here's b, that's 4. A is negative 1. There's a 1 there in front of the t. So negative 4 divided by negative 2 is just going to be 2, right? So we know the vertex is going to be at 2 seconds. What's its height? How do we figure that out? Well, in order to figure that out, we're going to have to plug it into the equation. So we're going to have negative 2 squared plus 4 times 2 plus 5. 4 times 2 is 8 plus 5. 2 squared is 4. Put the negative in front of it because all we inserted was a 2. The negative was already there. So If we combine the -4 and the +8, we're going to get 4 plus 5, which ends up being 9. We know that 9 is not as high as whatever this vertex is. Even though I estimated it, I don't need to know an exact because I already know that it's going to get higher than 9 just right here with this 10. So I know for a fact that the person whose potato pieces went higher were going to be Sam's, because Sally's only went up to 9. All right, whose potato pieces stayed in the air longer? Remember, it hits the ground right here when the time is 0 again, which is the x-axis. And so that means we need to solve the equation. I'm going to erase that just to have a little clear view. But this one, of course, is easier. Sam's is easier. His hit the ground after 3.5 seconds. When the height is 0, it's at the ground, right? So now, erase this so I can have some room. We have A equals -1, B equals 4, and C equals 5. Our formula is -b plus or minus square root of b squared minus 4ac. And that's all over 2a. Now, you could factor this if you wanted to, complete the square, or do any way that we learned when we were studying quadratic equations in order to solve this equation. However you find is easiest to find the solution, go forward and do that. I prefer the quadratic formula because I can just plug it into my calculator and be done with it. So -b plus or minus the square root of b squared minus 4ac all over 2a. All right, so I'm going to plug into my calculator square root parentheses 4 squared minus 4 times -1 times 5 close parentheses, and I get 6. So that means my new equation is -4 plus or minus 6 over 2 times -1 is -2. All right, so this means I'm going to break this with my plus and minus into 2 equations. One's going to be a plus and one's going to be a minus. So -4 plus 6. So I'm going to put in my parentheses in my calculator, -4 plus 6, close parentheses, divided by -2. And I get -1. Then I'm going to do the minus side. And I've got open parentheses, -4 minus 6, close parentheses, divided by -2. And I get 5. Now, which one makes more sense in my real world situation? After how many seconds will this potato pieces hit the ground? In -1 seconds or in 5 seconds? The answer is 5 seconds. You can't go back in time and have the potato pieces hit the ground then. So 5 seconds. So who's stayed in the air longer? Sally's did. All right. Can't get that line to mark go away. I don't know if y'all can see that mark. Use the 2 given functions to choose the best statement comparing the graphs. All right, so we have function 1, y equals 2x plus 4, and function 2, y equals 2x plus 5 minus 2. And it wants to know how they compare to each other in a graph here. So if we were to take a graph, the standard graph for an exponential function, this is going to be 0.1, 2, 3, 4. Okay, the standard exponential function, when 0 is raised to the power of 0, or if anything, be, let's say, just 2 to the power of x is what we'll graph here. To the power of 0, it's going to be 1. So that's the first one. Okay. If it's raised to the power of 2, it's going to be 4. And we have remember with exponential functions, we have what's called an asymptote. And our asymptote in this case is going to be x equals 0. So this is going to be our starting function. And then from there, we'll graph both of these because they both have 2x in them, right? 2x. And we'll see how these are going to look a little different. So let's start with 2x plus 4. How does this graph change when we add 4 to it? Well, everything moves up by 4. So this point 1 here is going to be here at the 4. And this one that is at x value 2, y value 4 is now going to be, the x value didn't change, but the y value is now going to be 5, 6, 7, 8. It's going to be right there. And where is our asymptote going to be? Our asymptote is going to be right here, 1 below the 1. 1, 2, 3. Oh, is that 4? I didn't put that up quite right. Let me erase these yellows and do that again. Boy. Looked like I had missed 1, 2, 3, 4. That was right there. And then 5, 6, 7, 8, 9. All right. So we're on moving up here. We want to move it up 4. I think I only moved it up 3 last time. So 1, 2, 3, 4. And then this one moves up 4 places as well. 1, 2, 3, 4. Now our asymptote is right here at x equals 4, right? And so our graph is going to look something like that. All right, so now let's look at the last function we have here. Y equals 2x plus 5 minus 2. So this minus 2 means that from our original graph, we're going to go down 1, 2 places. Let me draw a few more here. 1, 2, 3, 4. Okay, so we're going to go down 2 places, right? So that seems as if it's going to be 1, 2 right there. But you have to remember we have this plus 5, x plus 5. And since that's an inside function, remember it's going to be like ax minus h plus k. If you remember how we did these back when we were learning about exponential functions and how to translate them, it was what we called an inside function, meaning it happened to the x before anything else did. And so this is a horizontal change, and it's the opposite of what we see. Since this says in our equation plus 5, that means it's going to be, our h value is a negative 5, which means we're going to move left 5. So we already went down 2, right? But now we need to move left 5. 1, 2, 3, 4, 5. Wow, I didn't leave myself very much room. So this is our point from our original graph. Now remember, when we go over 1, that means we're going to go up. That's kind of more like right there. Let's try to be as accurate as possible. And where is our asymptote? On this one, it is right here. Remember, the asymptote is 1 below where that point is that we were finding. So this is our asymptote. And so the next point that we looked at was 1 over, and it's 1, 2, 3 up from this point. So 1 over and 1, 2, 3 up. So it's going to look something like that. Now, if you have a graphing calculator, you can plug this into your graphing calculator and look at it there. I'm going to show us, I think I have it up on Desmos. Let's see. Okay, so this is where we started. This is the y equals 2 to the power of x. Then here is the one that I did, the first equation that we had, 2x plus 4. And here is the third equation, 2 to the power of x plus 5 minus 2. And let's look at these points again. This is at 0, 1. This one is 0, 5. And here's this one is at -5, -1. So keeping those 3 points in mind, which are the same ones that I had when I hand drew these, but I wanted you to see it actually done by a calculator because this is what it would look like in yours. I want you to see, how does this blue graph relate to this green graph? Okay, well, we can see that if this point, we're just looking at this one point, how do they relate? So let's turn off this red graph for a minute because we don't need to look at that one. All right. So this is point 0 and this is point -5. So it's shifted left 5 between these two. There's a 5-point difference, right? And then if we're going from the blue to the green, vertically, what was the change? Well, this is 5 and then 6. And so it's a 6 down as well. So let's keep that in mind and let's switch back to our chart, or our worksheet rather. All right, so the graph 2's is shifted up 6. No, it went down. It shifted up 5 units and down 2 units. Up 5 and down 2. Up 6 and right 5. Right 5 and down. There you go. It can't be shifted up and down. That one was so confusing. Let me get a pen out and mark that out. You can't go up and down. Well, you could, but then that's not what we're doing. So it's not B for sure. You can't go up and down. This one has only up, so that's not it. All right, so this one's got down 6, this one's got down 6. So those are both in the wheelhouse of what we're looking at. Now let's think about, did we move to the right or to the left? Well, we said we moved to the left, so that's going to be D, because we went to the left and we went down. -2 is down, and then H being a -5 because it's the opposite of what we see is to the left. So you technically didn't need to do all the graphing that we did if you just look at this and you can see that we moved down and to the left. It's always good to know for sure though. Let's see. I cannot get this to, there we go, move. All right. Constructed response. A market researcher tracks the number of people who visit a company's website every month. The table shows the data from the last 5 months of this year. So the month and the website visitors. Which type of function, linear, quadratic, or exponential, best models this situation? Okay, well, not even considering the decimals, 5 to 12 is going to be 6. 12 to 25 is like what? More than 12, like what, 13? 25 to 52 is more than 25. It's like 28, 26, I don't know. 52 to, so it's definitely not linear. We definitely can see that it's not linear for sure. So it's not that. Quadratic. I don't want to look at quadratic next. I want to look at exponential because I did not do a definitive difference of difference 1. So I don't really want to look at a difference 2 right now. It looks like it's almost doubling every time, a little more than doubling. So I think what I'm going to do is just divide and see what's happening here. So 109.42 divided by 52.4 is, oops, 2.0881679. So let's say 2.09. And then 52.04 divided by 25.07 is 2.075. So 2.08. And then 25.07 divided by 12 is 2.089. 2.09. And then 12 divided by 5.74, just because I like to be sure, is 2.090. So it looks like it's 2.09, because we're rounding, we don't have an exact amount, but it looks like it's going to be pretty consistent. So we're going to say that this is exponential because it has a common ratio. All right, so practice or describe the approximate monthly growth demonstrated table by using words. So in other words, put what we just said into words, okay? So every month, the visitors grow by what? They more than double, right? Just a little bit more than double. But they do more than double because 5.74 doubled is, let's see, 5.74 times 2 is 11.48. So it's just a little bit bigger than doubled. Not much. You could probably say just every month the visitors double. It would be a decent description. You could say on average, every month that the visitors double. Assuming that the growth rate was the same for the entire year, give an estimate of the number of visitors of the website for month 7. Well, month 7 would be right here, right before 8. Since we're multiplying to get up, we divide to get down. So 5.74 divided by 2.09 is going to be 2.0. It says show your work. So we're going to say 5.74 divided by 2, not 1, 2.09 equals 2.746. So let's say 2.75. All right, estimate of the number of visitors. So the estimate is approximately 2.75 visitors in month 7. All right, and that is the end of our review worksheets. I hope you got them all right. If not, try again. Go research, find some worksheets to practice whatever you need to practice, whatever you need more practice on until you can get it right and it comes to you easily. Keep practicing, keep repeating, keep doing until you can easily complete all of these problems before you take the exam. All right.